The development of TE modes is mathematically very similar to the development of TM modes. In the transverse electric case, you have Ez equal to 0 because the electric field has to be transverse to the direction of the propagation Z. So, TE modes are characterized by having no component of Ez. However, this means that Hz must not be equal to 0, and it will also mean that Hx, Hy, Ex and Ey must all be functions of Hz alone. Okay. Now, how do we obtain Hz? Well, this was the first step in recognizing what components exist and what components do not exist. The second step would be to apply Helmholtz equation and solve this Helmholtz equation for Hz. Okay. The equation form will be exactly similar, therefore Hz will have sine of something x, cos of something y. We will not write down all those values, okay, you already know what those values are. However, what we need to write down is the form of Hz in terms of sine for x and y. Okay. Hz will have cos kxx, sine of kxx, so both forms could essentially be there, and then you have sine, or rather you have cos kyy and then sine kyy, right, multiplied of course by e power minus gamma mnz. You understand that gamma must also be having components m and n, which will then be related to kx and ky. You already of course know what is kx. Kx is m pi by a, whereas ky is n pi by b. I have not written down here just for notational simplicity. Okay. Also we know what is gamma mn. Gamma mn will be equal to, or this can be related to h itself. This would be equal to omega square mu epsilon minus kx square plus ky square, right, under square root. So we already know most of the things that we wanted to know. The amplitude for cos will be a, for sine it would be b, for cos here it would be c, and for sine it would be d. Okay. So this is the Helmholtz equation for Hz, Helmholtz equation solution for Hz in fact. So we have not written down the Helmholtz equation, but the equation would be exactly the same for what we wrote for Ez. You apply the variable separable criteria, you would then obtain this kind of an equation. Okay. So we obtained the expression for Hz. Now we run into a small problem. What is the problem? Well, let us try to apply the boundary condition for Hz. What should the boundary condition for Hz be? Does Hz go to 0 at walls? No, this is not true, this is wrong, because Hz happens to be the longitudinal component for the walls, and those components, you know, or the tangential components will not go to 0 at the waveguide walls. So what do? Here we need to either resort to a formal solution of Hz, you know, and then write down the appropriate Maxwell curl equation and then find out a new boundary condition for Hz, or we might recognize that del Hz by del x and del Hz by del y must somehow be related to Ex or Ey, correct? If they are related to Ex and Ey, and for those conditions we might want to obtain the boundary conditions, right. So it would be corresponding tangential or normal components which we can apply then. The upshot of all this very hand waving analysis is that at each of the waveguide walls we will apply the derivative condition, okay, or the normal condition. So del Hz by del n equal to 0, where n is the normal to the wall, okay, normal to waveguide wall. The philosophy behind the normal derivative of Hz being equal to 0 is simply that these normal derivatives will determine electric field and electric field components which will be tangential to the appropriate waveguide walls. If you really want to find what is this relationship, you have to go back to del Hz by del x, and you can see that del Hz by del x actually corresponds to Ey, and certainly this Ey component will be tangential at x equal to 0 and at x equal to a walls, and del Hz by del y corresponds to Ex component which would be tangential at y equal to 0 and y equal to b walls, right. So this would be the philosophy behind assuming that the boundary condition for Hz can be written not in terms of Hz itself but in terms of its normal derivative. This is called as normal derivative, where n is the normal to the particular component. Okay. Of course, Hz itself happens to be the tangential component for the waveguide walls, and that tangential component, derivative of the tangential component with respect to the normal, is called the normal derivative of Hz. So I will not actually solve this one. The solution is kind of very simple. Once you know what is Hz, you need to actually differentiate this one to obtain del Hz by del x and del Hz by del y, and appropriately substitute the conditions at x equal to 0, x equal to a, y equal to 0 and y equal to b walls. You do all those things and you will be able to show that b is equal to d is equal to 0. Okay. I will leave this as an exercise to you. The solution is very simple. You take del Hz by del x, you take del Hz by del y, okay, and then once you have found out this, you need to apply the boundary conditions at x equal to 0, x equal to a, y equal to 0 and y equal to b. So when you substitute all these values, and especially when you apply the boundary conditions at x equal to 0 and y equal to 0, you will find that b and d terms will go to 0. Okay. A simple thing to see that one here is because del Hz by del x will turn cos into sine, and that sine at x equal to 0 will vanish this component, but here it would be cos of kxx, that would vanish. So since this is vanishing, the only condition that this can vanish is when b is equal to 0. Similarly, you can show that d must vanish in this expression for Hz. Okay. It's a simple exercise, you try this out. If you don't get that one, we will give the solution during the notes that we upload. Okay. So now that we have applied these boundary conditions and obtained b equal to d equal to 0, we can proceed to write down what is Hz. Hz will also have some constants H0, but the dependence on x and y will be cos m pi by ax, cos n pi by b y. There would be components of e power minus gamma m n z that we may or we may not write down here. Look at this expression. Now you try to find out what would be the corresponding values of m and n for the lowest order mode to occur. Can we try the solution with m equal to 0, n equal to 0 or any of these combinations? Certainly you can try, because m equal to 0 turns cos of some 0 component into 1, n equal to 0 will turn the cos n pi by b into y term to 1, and both terms will ensure that Hz is still not 0, right. So substitute m equal to 0, n equal to 0, the expression for Hz becomes quite simple. You just are left with H0 e power minus gamma mn into z. So you just have a constant H0. Now the catch here is that this solution is also not alright, because Hz component might exist, but nothing will exist for Ex, Ey or Hx and Hy. Okay. So because these other components are going to 0, you will not be able to get m and n components go to 0. In the Tm case, what we had was Tm mn, neither m nor n should have been equal to 0. For TE case, the modes will vanish only when both components are 0. However, one of them can be non-zero. Okay. So you cannot of course have for the TE mn case m also equal to 0, n also equal to 0. However, you can certainly have for the TE mn case m equal to 0, n should not be 0, or the other way around, m is not equal to 0, n is equal to 0. You can have these kind of solutions. Okay. The fundamental mode for TE case turns out to be not 0 0 as we thought which would be, because the other components are not cooperating. The fundamental component for TE is that of 1 0 mode. This is the dominant mode, and by far one of the most important choice for a mode to be propagated. So if you take a waveguide, you kind of assume that it is to be excited so as to launch a TE 10 mode. Unless you are using these waveguides for filters, matching networks, other things, most likely you are interested in trying to put all of your energy into TE 10 mode. There are very good reasons for it. First of all, it has the lowest cutoff frequency, supports larger range of frequency operation, and third would be that this has the least amount of dispersion. Okay. So these are the different attributes of TE 10 mode, which is the dominant mode for a waveguide. So given a rectangular waveguide, this is the dominant mode for the rectangular waveguide, and for that mode it is interesting to just write down the expressions for electric and magnetic fields. For the TE 10 case, the Hz component will be some constant h0 cos of pi x by a, right. All the dependence on y is gone. There would be e to the power minus gamma mn z, that can be written as a common factor. If you go to Ex, you will see that Ex will be equal to 0 because that would correspond to differential of Hz with respect to y, whereas you will have Ey component that is non-zero. Ey is given by minus j omega mu. These constants are really coming from the earlier module where we wrote down the longitudinal components. So if you do not get these constants, do not worry too much, just understand what the form of the solution should be. Since Ey should be del Hz by del x, instead of cos it would become sine, the dependence on x would become sine, and again the y dependence drops out. Okay. So the y dependence drops out and you get sine pi x by a. Let me not write down the expression for or the dependence on z all the time. So what would be the other component that would exist? Interesting, you have Ey component, therefore the component that should exist must be Hx, and Hx component will be gamma 10 because you are really writing down the solutions for TE10 mode. So for the TE10 mode we can substitute m equals 1, n equals 0 and gamma is 10, and you will have component along sine. There are some additional components here, so you have H0 a by pi, okay, sine pi x by a. These are the three components that would exist for TE10. So if you leave out this Hz, this is almost like a plane wave wherein you have Ey and a minus Hx, right. So the ratio of these two should of course also give you the wave impedance for this particular waveguide. We will come to that one later. First, what is the cutoff frequency for this case? Cutoff frequency expression is the same whether it is TM mode or the TE mode. Now substitute m equal to 1, n equal to 0, it would be 1 by 2a square root of mu epsilon, right. So you remember this one, it was actually 1 by 2 pi square root mu epsilon m pi by a square plus n pi by b square under root. So now substitute m equals 1 and n equals 0, this b dependence goes away and m equal to 1 will pull out this pi by a here, pi and the numerator and denominator cancels, and this is the expression that you are going to obtain. We already have said that 1 by mu epsilon, 1 by square root mu epsilon is the velocity of the wave inside the waveguide. So you can even think of this, and in fact this velocity of the wave would actually be equal to the velocity of the TEM mode, not that is supported, but in a free space kind of a situation this would be the velocity, right. So this can be written as u of the phase velocity, or you can write down this as the TEM phase velocity divided by 2a. Okay. What would happen to gamma? Gamma 10 will be equal to j beta 10, assuming that your frequency is larger than fc10, and this would be equal to j omega square root mu epsilon 1 minus fc10 by f square, right. So this would be the expression for gamma. Okay. So we have written down the corresponding expressions for TE10. The last thing that I would like to write down is the expression for the surface currents at the walls. Again, as before, I will write down the surface current at x equal to 0, and in this case it would be x hat cross your h evaluated the surface. Now what are the h components? H components are x as well as z, right. So for the x equal to 0 component, x cross x will go to 0, but x cross z will give you a current along minus y direction, right. So you will have x cross z will be along minus y direction, and that would be h0, and that is exactly equal to the corresponding surface current. So Js is equal to minus y hat h0, substituting x equal to 0 will give you that one, and of course along z it would still go as e power minus gamma 10 z. For the case where f is greater than fc, this gamma 10 can be written down as j beta 10. Okay. So this is your surface current at the x equal to 0 wall, but what is the surface current at y equal to 0 wall? It would of course be the same surface current. For Js it would be the same surface current at x equal to 0 and at x equal to a because of the symmetry, but for y equal to 0 it would be y hat, that would be the normal from the waveguide wall. So y hat cross hx and hz, y cross x will give you a component along minus z direction, and then y cross z will give you a component along x direction. So you will actually get two components for the surface current, and you can evaluate this one by taking the appropriate cross product and then substituting y equal to 0 in those expressions. The answer that you get is h0 cos pi x by a along x direction, okay, minus some constant a, of course a by pi is the constant, gamma 10 is the propagation constant, sin pi x by a, and this one would be along z direction, okay. So this would be along z direction, e to the power minus gamma 10 z, okay. So for the x equal to 0 wall, there is only one component of the surface current, whereas for y equal to 0 you have additional components for the current, okay. You can also sketch the TE10 mode or TE11 mode. We will not do those sketches, you can actually find out them from your textbook. Let us try to solve one problem before we go on to the next topics in the waveguide. We want to consider a waveguide which is widely used, which is called as WR75 waveguide, okay. These numbers are just the numbers which would tell you the ratios of A and B. For this waveguide, which is filled with air, so the waveguide is filled with air, which means that mu is equal to mu 0 and epsilon is equal to epsilon 0. The dimensions of A and B are A is 1.905 centimeters and B is 0.953 centimeters. Assuming that the waveguide itself is perfect, find the cutoff frequency for the TE modes and also find out what is the range of frequencies over which only this mode exists. That is, if you assume f is increasing, at some point you will reach the cutoff frequency for 10. Here you will start having propagation, and after a certain point you will start to have higher order modes, okay. So the range or the bandwidth over which there is only one particular mode, that is you will have only TE10 mode, is called as the dominant mode range or dominant range, okay. Dominant range is the one in which only TE10 exists, all other modes are absent, okay. What is that particular dominant range for this waveguide? Well, the answer would be that you first find out what is the cutoff frequency for TE10 and then try to find out what is the next order mode, okay. Once you find out the next order mode, you can find out the cutoff frequency there, and that difference will tell you what is the dominant range. First of all, the cutoff frequency for TE10 mode, which is the lowest order, is given by the phase velocity UTEM divided by 2a. I know that the waveguide is filled with air, therefore it acts like a free space itself. So this fellow is C, and C is 3 into 10 to the power 8, 2 into 1.905 into 10 to the power minus 2, and you will see that the cutoff frequency is 7.87 gigahertz, okay. Now what is the ratio of A by B? A by B ratio is 1.99, and once you find that the ratio of A to B is actually greater than square root of 3, okay, this is greater than square root of 3, the dominant region would happen when the next higher order mode, if you find out, that would be TE20 mode, okay. For a waveguide in which this particular case, the ratio of A by B is greater than root 3, the next higher order mode is TE20, after that comes TE01, then comes TE11, okay, then comes TE11 and TM11. So the magnetic transverse magnetic mode does not begin to propagate until a few TE modes have been already propagating for the case of A by B greater than square root 3, okay. So for this case, the next cutoff frequency would occur at FC20, and for that one can find out, and that would simply be multiplying the original frequency FC10 by 2, which would be equal to 15.74 gigahertz. So the range of frequencies over which you will have the dominant mode would be over the case where 7.87 to 15.74. Although at 7.87 you really don't consider the waveguide to be propagating, because you are really at the edge of the waveguide. So you take some amount of frequency. So here you have, this is FC, but you will actually wait for some other factor before you consider the waveguide to be operating, right. So this frequency range at the end or at the band you would avoid, because you do not want to have components which are just cutting down over here. So you avoid some percent, say let us say 25% higher than FC10 would be the range over which we operate. That is a very good thumb rule, and you will also operate at the lower cutoff frequency mode for the given wavelength to be around. So if this is your range, you would operate them at 0.95. So you would actually operate anything between the range of the next higher order mode. So just about here. So if this is FC20, then you just go to 0.95 FC20 and you start at 1.25 FC10. To avoid, I mean this is just an engineering thing, obviously there is not a reason mathematically that you have to take this as the usable range. The usable range for this waveguide is chosen in such a way that you are just above the cutoff frequency, so that your wave component, I mean frequency components are not getting attenuated because of the lower order, and you are not getting cut off because of the next higher order mode. Okay. So if you calculate the usable range according to that, usable range for this example would be 1.25 times 7.87 gigahertz, okay, to 0.95, 5% less than the next higher order mode, which is 15.74 gigahertz, and numerically these values turn out to be 9.84 gigahertz to 15.35 gigahertz. So you have about 5 gigahertz of bandwidth roughly, and this bandwidth is the bandwidth over which only TE10 modes can be propagated, or in the frequency range only TE10 modes exist, and they would be propagated with whatever the characteristic propagation for TE10 is concerned. We will stop at this module. In the next module we will consider some associated terms for waveguides, and then quickly perform a simple calculation for the waveguide loss, and we will close a chapter on waveguides. Thank you.